In class, we have been discussing the mathematical curiosity that if a number is divisible by 3, that the sum of its digits is also divisible by 3. Now, one of the things that we just talked about and showed to be true in class is that this is not necessarily true for all ways of writing numbers. In other words, it's peculiar property of the fact that we are writing our numbers using a base 10 formulation. We write our numbers using a different kind of formulation. It will not necessarily be true that the sum of the digits is divisible by 3 when the number is divisible by 3. And in the process of giving some examples, we would write the number 9 as being equal to 10 minus 1. Let's go through this a little bit. I want to do another step along the way of showing that this peculiar mathematical property in base 10 is true for all numbers written at base 10. Okay, now if we look at the number 10, 10 minus 1 is equal to 9, and 9 is divisible by 9, and it's divisible by 3. Now on this slide I show 10 squared minus 1 is equal to 100 minus 1, which is equal to 99, and 99 is divisible by 9 and divisible by 3. 10 cubed minus 1 is equal to 999. That's divisible by 9 and divisible by 3. 10 to the 4th minus 1, 9,999, and so on. You get the idea. So the question I am going to be asking here is that will it be true that in general, if 10 raised to the p power, where p is an integer, 10 to the p minus 1, will that always be divisible by 9? Okay, and we will show that how we can see that that is true. Okay, now first of all, I'm going to begin this exercise with the assumption that we know that, look at the top line here, that we know that 10 raised to the p minus 1 power minus 1 is divisible by 9. We know that that's going to be true for some value of p. In fact, we've just shown that, for example, that 10 squared minus 1 is divisible by 9. Now, if we know that's true, can we show that it must be true that 10 to the p minus 1, the next increment on the exponent, 10 to the p minus 1, will be divisible by 9. So, for example, if 10 squared minus 1 is divisible by 9, must it be true that 10 cubed minus 1 is divisible by 9? And the answer is yes, and I'll show you how we can prove that. And I'm going to do it using the technique of synthetic long division, which I hope you're familiar with. If not, we'll have to discuss it in class. So I want to look at 10 to the p minus 1, see if it's divisible by 9. Look at the left-hand side of the equal sign at the bottom expression. We have 10 to the p minus 1 divided by 9. Or I've written as 10 to the p minus 1 divided by 10 minus 1. Okay, now we write it in a synthetic long division form on the right-hand side of the equation. So we go through that exercise of synthetic long division, as I've shown it here. The right-hand side of the equation, as we divide into 10 to the p minus 1 divided by 10 minus 1, I say, aha, okay, the first term in that synthetic long division on the top is going to be 10 to the p minus 1. So we're going to have to take 10 to the p minus 1, multiplying the number on the left to give us the number written in red, which is 10 to the p minus 10 to the p minus 1. And we're going to subtract that from the number above. So we do that. We have this expression as shown right here. We're taking 10 to the p minus 1 and we're subtracting from it 10 to the p minus 10 to the p minus 1. And we do that, we get the number written in red below it. When that comes about because the 10 to the p from 10 to the p is 0, but we're subtracting a negative 10 to the p minus 1, so that makes the number in red a positive 10 to the p minus 1. And then we're subtracting that above, there's a negative 1, the negative 1 comes down. So the number in red is what we get after we do that step of the synthetic long division. And what is peculiar, if you remember, is that our beginning premise was that the term 10 to the p minus 1 is divisible by 9. In other words, divisible by 10 minus 1. So now Another way of writing out that synthetic long division is to write it out in this fractional form right here. The left-hand side is our original problem. It's 10 to the p minus 1, all divided by 9, or divided by 10 minus 1. The right-hand side of the expression is what we get from doing the synthetic long division. We say that's equal to 10 to the p minus 1 plus the fraction 10 to the p minus 1 divided by 9, which we've written as 10 minus 1. Now remember that our premise beginning was that the numerator of that fraction on the right of the plus sign, the 10 to the p minus 1, that's divisible by 9, which means if we divide it by 9, the result is an integer. Okay, there's no remainder left over. That's what it means to be divisible by. So the term on the right-hand side of the plus sign is an integer. Now on the left-hand side of the plus sign we have 10 to the p minus 1, but remember p is also an integer. It's a number greater than 1. So that means that 10 to the p minus 1, 10 raised to some power, okay, 10 squared, 10 cubed, and so on, that is also an integer. So the expression on the right-hand side of the equal sign is the sum of two integers, which means that number, that expression on the right-hand side of the equal sign is an integer. So we have that the expression on the left side of the equals, the 10 to the p minus 1 divided by 9, is equal to an integer. That means, then by the definition of what it means to be divisible by, that the expression 10 to the p minus 1 is in fact divisible by 9, or as we have shown it here, is divisible by 10 minus 1.